All right. Our problem of the day last night was our first foray into biochemistry. How many of you guys are planning on doing biochemistry? All right. That's a good chunk of you guys. Biochemistry is really fun. Biochemists and chemists think about carbohydrates slightly differently. Chemists like to think of carbohydrates oftentimes in the open chain form, because if you think about their reactivity, they're aldehydes, right? The closed ring forms don't look like aldehydes, but glucose, for example, behaves like an aldehyde. So in this problem, I was first asking you guys, how are the two closed ring forms related to one another? What do you guys think? Diastereomers. So if you look at this position here and this position here, we have different stereochemistry, right? So one stereocenter was flipped out of all of them. They're definitely not enantiomers because they're not superimposable mirror images. So the one on the right we call alpha D-glucose. And what that means is that it's an axial group sticking down. And then the one over here, we've got beta D-glucose. We're going to cover carbohydrates at the end of the term, but I just wanted to kind of touch on it because it is very closely related to this chapter. So these are diastereomers. Specifically, whenever you switch only one stereocenter, they're oftentimes called epimers. So you may hear that word thrown out occasionally. That just means one stereocenter was flipped, but it's in reference to diastereomers. All right. And then if we're looking at the closed ring forms, is there some sort of unique functional group in there? It's going to be a hemiacetal. And some people are a little confused on what the difference is between a hemiacetal and a normal acetal. The easiest way to distinguish them is to ask yourself how many times the nucleophile got added in. In this case, the nucleophile only added in once. So now let's do the mechanism. Oh, sorry, I gotta practice my chair drawing here. Yep, the ACS exam is all multiple choice.
Well, how will we do like synthesis?
It'll give you multiple choice synthesis problems. All right, so the first step, we've got some sort of acid around. So I'll draw this as HA. We normally use something like sulfuric acid or tosalic acid. And we protonate our carbonyl. That gives it a positive charge. And we've still got these hydroxyl groups. All right, and then the key is this alcohol is going to be the nucleophile. Why?
Because it's the closest proximity.
Well, it's proximity, but why doesn't the alcohol above it attack in? It wants to make a six-membered ring. That's key for this. We know in organic chemistry, six-membered rings are highly favored. So this alcohol will attack in. Oop. Let me fix this. That'll stick this alcohol out here. Now we've got an oxygen that's positive. So what's our next step? What do you guys think? Deprotonation. And you can do this with your conjugate base or potentially with another alcohol group.
Professor, yeah, you did show one step.
I showed what one step?
You showed, but you didn't show the lightning of that electron. So if you're going to do it like that, I think you need to indicate which arrows going first.
So remember, you can draw resonance structures if that helps clarify it for
I
you.
understand that, but in your drawing, it's not clear. You're saying that elevation or that nucleophile can attack that carbon. It's not going to do that until after it denucleophilizes.
Not necessarily. Remember, a resonance structure isn't flipping back and forth. It's a hybrid version. You can draw either one.
But well, then why would it attack positive and oxygen? If
Uh,
it's nucleophile, why is it going forward?
Because then you'd form a very, very unstable oxygen-oxygen bond. Yeah.
Still, I don't understand why you don't have to show the delocalization on that.
So remember, with the resonance structure, it's not that one picture is more correct than the other. It's that it's a hybrid of the two. You can draw it using either representation. It's perfectly fine to draw a resonance structure using one or the other representation as long as you're following all of the rules, like you're not violating any Texas carbon rules or anything like that.
Are you going to make the greatest down if you didn't do the double arrow?
What whole arrow?
Like,
It is important to remember that it's an equilibrium because this is driven by pH. If you do a single arrow this time, it's fine. Just remember all of these nucleophilic additions for the most part are reversible with the exception of things like a Grignard reagent.
so when you're using this oxygen,
Yep, oxygen nucleophiles are very reversible. Specifically, if we want to go back from our hemiacetal to our open chain form, what could we add into this? Water, right? So oftentimes we can reverse acetal or hemiacetal by adding in a bunch of water and use the Le Chatelier's principle to push the reaction backwards.
Would we have to know the mechanism for Americans?
Yep.
Okay, and also when we draw this, can we just use the generic HA, or do you want us to use specific?
You can do generic HA, that's fine. I know it can save time, especially if you're trying to hurry. Yep.
are we going to have labs
Are we going to have
like this for this?
a lab?
Yeah, with these kind of genes.
Not in 263. You might have some carbohydrate chemistry and biochem. Yeah. Okay, so now let's go back to chapter 20 and switch gears into nitrogen nucleophiles. Yesterday we hit all of the oxygen nucleophiles. And it depends on what nitrogen nucleophile you're using. So we're going to break this into two sections. The first one's going to be primary amines, and then we'll continue on into secondary amines. Primary amines. The overall reaction for this is pretty simple. I'm going to draw a generic aldehyde. You can react this with H+, meaning catalytic amount of acid. You can react this with, let me actually change the color of this R. And you can remove water from this reaction. And when you do this, you form a new functional group. And this is called an imine, starting with an I, so I-M-I-N-E. And the mechanism is pretty similar to what we've seen, but I also wanted to bring up an important note. And this was something that somebody was asking me in the hallway too. And it was about pH. And pH is very, very important for a lot of these reactions. If we have this too acidic, what will happen? So first thing we'll do is we'll protonate our oxygen on our carbonyl. But if we've got really, really strong acid around, what could happen? Yeah, you protonate your amine. If you protonate this amine, it's no longer nucleophilic, right? So we have to maintain a really careful control of our pH. And in particular, the pH for this reaction should be about 4.5. Otherwise, you end up protonating your nitrogen on your nucleophile and the reaction won't work. So this is one of these organic reactions where you do have to pay attention to the pH, and you usually run it in a buffer system. All right, so now let's go through the mechanism. All right, so we start out with our generic aldehyde. We've got our acid. I'll label this HA. We can show the carbonyl getting protonated, kicking off our conjugate base. Now we've got a really good electrophile. We can draw the resonance structure like Kareem was saying, or we can leave it as is. You're fine doing it either way.
I mean, one is clearly more accurate, though.
And I'll label the R group here as a blue R. So we've got our primary amine that can attack in, kick up electrons onto that oxygen. And we have to keep track of our charges too. That was one thing I noticed on the problem of the day. People were losing track of their positive charges and their negative charges. Those are really simple things to get doctor points on, so try to make sure you count all of your electrons. The next step, we've got our conjugate base that can deprotonate our nitrogen, giving us our neutral molecule, and we can regenerate our acid. And then we have our acid hanging out that we regenerated, so we can protonate our alcohol. Just like we saw with the acetal reaction. That turns that alcohol into a very good leaving group. And does the alcohol fall off on its own? Or the water in this case? It kicks it off, right? I always use the term maliciously shoved off just to emphasize the fact that it's not an SN1-like reaction. It's more SN2-like in that it's getting shoved off. Okay, now we're getting close to being done. We've got our nitrogen that's bonded to a hydrogen, and it's got the R group on it. But again, we have to keep track of our charges. We've got a charge right there. And we've kicked off water, or you can show your conjugate base acting as the base. So the final step is you have your base come, grab this proton, clamp down. Oh, let me slide this down a bit. And you end up with your final imine. And it's important to remember that we are generating water in this reaction. So if we want to drive formation of the imine, what can we do? Remove the water. If we want to go back to our aldehyde, what can we do? Add water. So you can drive position of the equilibrium by how much water is around. All right, let's do an example problem. In this case, let's start with the ketone. Oh, that's supposed to be a cyclopentane ring. There we go. Let's try to figure out what our product would be for this reaction, and we're going to do this with catalytic acid. So I'll draw an H+, and if we want to drive it forward, we can do minus H2O. You can draw out the full mechanism, or you can just try to identify the trend. Do you guys want to see the full mechanism? Yes? Okay. So let's actually do this. I'm going to erase this. You guys can leave it on there, but I want to show the full mechanism now. So first step, we don't want to protonate our primary amine. We just want to protonate our carbonyl. Kick off our conjugate base. Get a positive charge on there. You can have your primary amine attack in, kick up our lone pair onto our oxygen. We have a positive charge on there. So the next step would be our conjugate base, which can come and deprotonate our amine. Push down electrons. That'll get rid of that positive charge on there. I guess I kind of rotated it, sorry. There we go. And we've regenerated our acid. Which can be used to protonate our alcohol. Turn it into a good leaving group. Now what's the next step? A malicious shove, right? By the nitrogen lone pair. Kick off our water. I'm going to scroll down. Kicked water off. Now what's our last step? Deprotonate, right? So we've got our conjugate base. And we can end up forming our final imine. Plus we end up with our regenerated acid. Oh, and this one I just had this molecule rotated a bit. So they're both coming off of the same carbon, both I just rotated the hexamer ring slightly. Sorry about that. I didn't want to have to erase it and redraw it. So these are pretty useful reactions. Like I said, with acetal, hemiacetals, imines, any of these, if you add water, you can drive it in the reverse direction. All right, now let's switch gears and talk about secondary amines. Because the mechanism is slightly different. Oh man. Amines. All right, the overall reaction looks pretty similar, but our double bonds moved. So I'm going to take a generic aldehyde. I'm going to add in a catalytic amount of acid. But this time we're going to use a secondary amine. So we've got two different R groups coming off of it. And our final product has R groups coming off of that top nitrogen, but we end up with a new alkene. So instead of calling this an amine or an imine, we call it an enamine. So we start with the prefix "ene" as in an alkene, and then it's an amine, so it's an enamine. Pretty simple concept. Let's do the mechanism for this. So the first step in all of these reactions is going to be protonation of our aldehyde or ketone. So I'll draw HA in here, where the ketone can attack end up with a positive charge. Next step, we've got our nucleophile that can add in because we've made our electrophile very good. So the nucleophile will add in, push up electrons onto that oxygen. And then we've got these two R groups dangling off now. And the nitrogen has a positive charge, so we can't forget that. And then we've got our conjugate base. This conjugate base can deprotonate our amine. And we're almost there. What do you guys think the next step is? Protonation of the alcohol, right? We want to turn that alcohol into a good leaving group. And we just regenerated our acid, so we'll take the proton back from the acid. Turn that water into a nice leaving group. And we have these two R groups still on there, and the lone pair on the nitrogen. Next step, a malicious attack. Gets shoved off. So we end up with our new double bond to our nitrogen. Whoop. Sorry. The R should be blue. I'll try to make it nice and consistent. Okay, so we're not quite done. We can't deprotonate the nitrogen, right? There are no protons to take. But what can we do? So the R groups aren't good leaving groups. They're going to hang out on that nitrogen. Yeah, we can steal a proton from that methyl group, right? So the next step is, if we've got our conjugate base, we can show it stealing one of these protons, which will clamp down and push electrons up. So it's almost like a Jacob's ladder. And you end up with both of your R groups, and you regenerate your acid. And this, we said, was our enamine because we've got an alkene. We don't have a nitrogen-carbon double bond. So the main difference is your enamine, you would have your double bond between the carbon and the nitrogen. Your enamine, you have the double bond between two carbons. So it's a subtle difference, and that's because the secondary amines don't have a proton that can be removed in order to get to an imine. Yep.
Does it matter? It's going to be probably a stupid question, but does it matter about R groups if they're the same or not?
Usually they're the same, but occasionally you can get mixed systems. The reason people avoid mixed systems is that then you run into stereochemistry problems. So let's say these R groups are different. You could get some where this R group is cis to that. You could get ones where they're pointed away. There is some resonance delocalization, so this doesn't have completely free rotation. But normally they're the same R groups. You'll see that in the book in most practice problems. Yeah. All right. Do you guys want to see an example with enamine synthesis? Okay, so we'll do an example of this. Oop. I like this example. What's this starting material called? You could call it diethyl ketone. What if we're using the formal IUPAC naming? What's the longest parent chain? It's a pentane. 3-pentanone, right? So we could start with 3-pentanone here. Or penta-3-one, or pentan-3-one. Either one is acceptable. And in the first step, we're going to react it with some acid. Actually, let's do HA. Kick off our conjugate base. All right, and this time we're going to use diethylamine as our nucleophile. So I'm going to abbreviate diethylamine using the ET nomenclature. So we'll draw the nucleophilic attack from the nitrogen, kick up electrons. Let me actually draw the full ethyl groups, I guess. There we go. All right. What do you think the next step is? Deprotonation. So I know these reactions get really, really steppy, but it's important to remember all your protonations and deprotonations. Okay. Now we've regenerated our acid. What do you think the next step should be? Protonation. So this is really an elaborate proton transfer from the nitrogen to the alcohol. And then next step, malicious shove. We'll take the lone pair from the nitrogen, kick it down, pop off our water. And we generated water here. I'll put this in brackets. And then we've got our conjugate base. Now what? Are we done? No, we've got a charged molecule. What's the very last step? Remove a proton. Do we remove a proton from here? No. Exactly. We have to remove a proton from the correct position. So we grab this proton, clamp down, push up electrons. And we get this bow tie looking molecule. Oops, sorry. Plus HA. And we said that this is an example of an enamine. All right, let's take a look at a couple other unique nitrogen nucleophiles. You see them in a handful of situations. You guys need me to scroll up? Okay. All right, the first one is still an amine, but it's also got an alcohol on it. It's called hydroxylamine. So if you have a generic ketone and you react it with your catalytic acid, well, you end up getting an imine or an enamine. An imine, why is that? Yeah, because you've got a primary nitrogen. So in this case, what you get is something that's called an oxime. It's an imine where that R group is changed to an OH group. These are commonly seen. The other that we'll talk more about, what's that? You may see the names in your books or in the sapling problem, so it'd be a good idea. Name the reactions? I would ask you to identify imines versus enamines for sure. The next one uses rocket fuel. This is hydrazine. Very, very flammable. Will this form an imine or an enamine? No? An imine, but again, it has a unique name. It's not an amine. It's called a hydrazone, and this is mostly due to it being reacted with hydrazine, so they call it hydrazone. So this reagent is hydrazine. So the product gets called a hydrazone. Does hydrazone look very stable?
Yes.
No.
You've got two nitrogens next to each other. What do two nitrogens next to each other want to become? A gas, right? So anytime you see nitrogens bonded to one another, there's usually a way to drive them off and form nitrogen gas. Yep.
What's the conjugate base for these reactions? Because we're just using generic.
So remember that H plus, that catalytic acid, is usually sulfuric acid or tosylic acid. You don't want an acid where the conjugate base is a good nucleophile. Otherwise, you run into mixed products.
When you say H plus, you want us to use little.
It's implied that it's tosylic or sulfuric. If I were to ask you to identify the acid, you don't want to list HCl because otherwise you'd have chlorine that could add in and act as a nucleophile. Okay, so let's go back to the hydrazone reaction and go through the mechanism a bit. But before we do that, let's talk about a new reaction. Wolffe-Kichler reduction. And this involves a hydrazone intermediate. So we'll go through and see the whole mechanism for this here in a second. But let's say you've got a generic ketone. You react this with your catalytic acid, and then you react it with hydrazine. You'll form your hydrazone. Plus water. And then the next part is a little bit different, and we'll walk through it. You take sodium or potassium hydroxide and water, then you heat it. And you can actually pop off a carbonyl group and go straight to the alkane. So this looks pretty similar to the Clemmensen reduction, right? And those were for aryl ketones, but this will work on normal aliphatic ketones as well. What was that?
Does it blow up when you do that?
No, it's kind of cool though, because when you create nitrogen gas, the solution starts to bubble, and that's how you know it's working. And when it stops bubbling, you know it's probably done. So it's a nice, quick, easy reaction to watch. So let's do the overall mechanism. And I'll do the imine formation as well, just for practice. So first step, we add in acid. We can protonate our ketone. So let's draw our arrow pushing there. Next step, we've got hydrazine that can add in as a nucleophile, kick up electrons. And then we've got a base that can come grab a proton off of our amine, clamp down onto the nitrogen. We recreate our acid. So the alcohol will come and grab a proton from the acid. The next step, what do you guys think? The malicious shove. I'm going to really pound this onto you guys this year because last year my students always drew the water falling off as the first step and then drew it clamping down. It's a concerted process.
I'll be looking for that term on the ACS.
The malicious shove.
Yeah.
It's not the malicious shove, it's not the right stuff. It's just wrong.
And we generate water as our byproduct. And then we've got our conjugate base, which can come grab our proton. And we're almost through this very long synthesis or mechanism. This is about the point in time where your hand starts to cramp. And this is our hydrazone. So you can, if you want, try to stop there. But now we're going to continue on to step 2 in our synthesis. All right, next up we've got potassium hydroxide around, and we know that acid-base chemistry is the fastest. I'm going to actually draw out these hydrogens too. So the hydroxide will come and grab one of the amine protons, and it will dump electrons back onto the nitrogen. A nitrogen with the lone pair doesn't look very happy to me, or a nitrogen with a negative charge, I should say, doesn't look very happy to me. But why is this somewhat stable? There's a resonance. So we can say, well, this can actually delocalize electrons there, and then share it with that carbon. That carbon has a negative charge. We'll bracket it in to show that they're resonance structures. Next up, we've got water around that was formed during the deprotonation. So this can grab a proton off of water. And then we can repeat this whole process. Where the hydroxide can come and deprotonate that last proton off of the amine, clamp down electrons, and then move that down to the carbon. Actually, let's change this from a double-headed arrow to a single-headed arrow. Sorry. And why did I change that?
It's not going to come back down.
Yeah, once you form nitrogen gas, it's going to bubble out of solution. You're going to drive the reaction out of equilibrium. And when you do this, you end up with another negative charge plus N2 gas. This is a really, really strong base. And you, in this case, end up with cyclohexane as your final product. So it's a really, really steppy reaction, but it's a very useful reaction. Why might this be preferable to the Clemenson reduction that we saw before? Yeah, it avoids the use of mercury, and the Clemenson reduction really only works well for aryl ketones. This will work on practically any ketones. And this is very nice because you're avoiding use of any heavy metals. And you can drive it out of equilibrium by having your nitrogen bubble away. So it's a pretty clean reaction to run. All right, let's do some practice problems. You guys want me to leave this up for a second? For 5 minutes? All done? All right, so let's switch to practice problems. So give the starting material and reagents. And I'll give you guys the product. So essentially what I'm looking for is for you to fill in this box, fill in the reagents above the arrow, and we're going to form this bicyclic system. Let me fix my ring here. That's good enough. So the first thing I do when I see the product is I try to identify whether it's an imine or an enamine. What is this one? It's an enamine. All right, so we can classify this as an enamine. We know that we always need a catalytic amount of acid. We need to remove water if we want to drive this to completion. What's our amine that we need?
Whatever that is called.
It's a secondary amine. Try to figure out if you can identify what it should look like, though. So it's like cyclopentane, but with the nitrogen? Yeah, I'd say that's very correct. So if you look at it, that is this entire group that got added on. And it's so remember, if it's a secondary amine, you can't deprotonate this at all and form an enamine, so you can't get a double bond there. So the question is, what's our starting material look like? It's going to be a ketone, right? Cyclohexanone, exactly. This would have been on my exam. It would have had a little 3 in there. So in this case, if you look at the connection, this portion of the molecule is right here, and then the enamine was formed right there. All right, let's do another one really quick before we have to head out. I may even leave this for you guys to think about, and then we'll cover it in class tomorrow. Or, sorry, Monday. All right, is this an imine or an enamine? Enamine. All right, so I'll let you guys think about this for a while, and then when we come back to class on Monday, we'll go over this last practice problem and maybe do a couple more. All right, other than that, have a good weekend. Email me if you have any questions. If there's a sapling problem that doesn't make sense, don't be afraid to email me. I can even reset it for you if it's just being troublesome.